Okay, so let's start today's lecture. Okay, so we have reviewed the mechanics of materials. How was the exam? No good? Finished? Let me see. OK。你有登记了？那你知道有一个东西叫低中高？啊，OK，照相过了。啊，OK。You can take it back. What's the average? Oh, 4, okay. 10 out of 10, the average is 4. You can take it back. Yes. Okay. Out of 10, average is 4. As expected. I thought this is gonna happen. Okay, anyway. Tomorrow's lecture, I will show you the solution process. Okay. But based on the syllabus, I'm supposed to give you, or maybe we can talk about it right now. Yeah. So, yeah, so we can swap between tomorrow and today. Okay, so the solution is, okay, we can talk about the solution. This is a solution. So the problem, let's open the problem as well. Here's the problem. First one should be very easy. Basically, Mohr circle. Okay? And let's take a look at the solution. So draw the Mohr circle. If you stay on the right-hand side of the element, you have a positive tensile stress, which is 70 megapascal. So over here, on the horizontal axis of the Mohr circle, which is stress, normal stress, you have I did it wrong. No, I didn't do it. Oh, here's the 70. Okay, I'm good. So I scared myself. Sorry, I scared myself. Okay, so this point right here, there's a dot. That's 70. And based on my drawing, if I treat the counterclockwise shear stress as positive, then over here I have a clockwise shear stress, which is 45. So this should be negative 45 megapascal in the Mohr circle. So over here, you go down by there's a negative 45. So this is a first point. So that particular point is basically the point on the right-hand side. So this is your point A, and this would be your point A. Okay. Now I take a walk and move to this point B. Over here, I already make a 90-degree turn. And in the Mohr circle, I will be making a 180-degree turn. And right here, there is a compression stress, which is 30 megapascal. Because it's compression, so it's gonna be negative 30 in the Mohr circle. So that's why there's a negative 30. And over here, you have clockwise shear, 45 megapascal, so positive 45. So this will be your point B. Okay, with these two, you can already draw the circle. The question asks you to find the principal stress. So the easiest way is to find where is the center point. So the center point basically over here is 50. So the total right here is 100. So half of it is 50 right here. And because this is negative 30, so this should be 20. So this is the center, okay? And of course you can take the average. Then how do you calculate the radius? Here is 50, here is 45, then this is your radius. So radius will be the square root of 50 squared plus 45 squared. The answer will be 67.27 megapascal. I ask you to write down the unit. So please write down the unit. That will be exactly the same amount as your tau max. Okay, so that value basically is your tau max. So how do you compute for the principal stress 1 and principal stress 2? From the center plus radius and minus radius, that would be your principal stresses. So from the center plus and minus the radius, at the end you have 87.27 and negative 47.27 megapascals. That's already principal stress, maximum shear stress, and already draw the Mohr circle. Write down. You need to write down calculations and mark your solution with units. That's everything I'm looking for. So if you know how to do it, you can finish it within 5 minutes, right? Very, very easy. Okay, now, question, go ahead.
By tau max, you have like the root of 50 power of 2 plus 45 power of 2. And should the 50 not divided by 4? Because on the slides, tau max is like the root of sigma A power of 2 divided by 4 plus tau A in the power of 2.
So you memorize the equation?
I had it just like here.
I mean, why memorize the equation? I never memorize equations. I mean, that's wasting your brain. Okay. Let me see. Let me find it. Where is it? Oh, this one. Lecture. Which one was it?
Lecture 2, yes.
Okay.
On page 10.
This one?
Yes, this one. The first tau max is the root of.
Okay. This is basically this value minus this divided by 2 and then take a square.
No, the equation, yes.
This one.
This one, yes.
Yeah, so this value minus this divided by 2 and then take a square.
I did it that way, but
So if we do, so maybe my note was wrong. I mean, who memorized? Don't memorize equations. Okay, this minus this, that would be 100. 100 divided by 2 is, this minus this, that's 100, right? Divided by 2 is 50.
okay, all right.
That is right. Don't memorize it. Those are not necessary. It's a geometrical problem. You basically find the radius. So from geometry, this is 50, this is 45. Draw a triangle, and then okay, I need to calculate uh, the length right here. So simple math. Don't memorize it. So from here, I don't even remember this. I just from geometry. Because I think from the note, this part is plus, this part is negative. So then, if you just memorize it, sometimes it's confusing, and sometimes you have positive value, you have negative value. You can be making mistakes more easily if you insist to follow the equation. Okay. Okay. Now, the second problem, okay, it's a beam problem. So from the beam, first of all, you can now make a drawing of this, where you have a reaction force of F1 on the middle of the bearing, and the reaction force of F2 at the middle of the bearing, pointing up. Based on my drawing, it's pointing up. So now I'm going to use balance of moment. And the first equation basically comes from choosing this F1 point as the support, as the center, and figuring out the clockwise moment contributed by this distributed load. That would be 35. It's a line force. So you need to multiply the distance to figure out what's the total force. So 35 times 40, that's the total force. And what's the radius, distance from the force to the center? Basically 80 plus half of 40, so 100 here. That's the distance. That's clockwise moment. How about the counterclockwise? So only F2 times the sum of these three distances. So I did some math, so that would be A2 3.53. Right? Similarly, you can treat the F2 point as the center point, and then similarly, this force contributes the counterclockwise moment to the center, and the F1 contribute clockwise moment. So over here again, 35 times the distance, the width 40 right here, multiplying 50 plus 20, half of this. So that's the distance from the force to the center. F1 times the distance, total distance, 80, 40, and sum of 80, 40, and 50. At the end, F1 equals to 576.47 Newton. So that would be the calculation for reaction forces. I didn't ask you to do it, but you need them. So this is just part of the calculation. Once you have that, you can then work on this shear diagram as requested by the problem. So I'm taking a walk from the left. I meet F1 pointing up with the amount of 576.47. So I have a positive shear force. Then moving forward toward right, the shear force remains the same until I meet the distributed load going down. And because this is a constant distributing load, so my shear will be gradually decreasing in a linear fashion. So what's the slope? The slope will be the same as the amount of W, but it has to be negative because it's not going down. So the slope is negative 35. Okay, so there's a linear equation right here. And it keeps going down until your walk stop at this 120 millimeter position. So this is where it is. And no more forces. So the shear force remains that amount until you meet this edge, 170. And there is a reaction force going up. So A23.53 going up, and it goes to 0. And there are no more forces at the end, right edge. No more. So remains 0 on the right. And if I now try to write down the equation for these three different parts, the shearing force for the first part would be constant value 576.47, and the last part would be constant negative 823.53. And at the middle right here, I know the slope is negative 35. X plus some constant C1. So I need to compute for the C1. How do I compute it? I just plug in position 80, plug in, and I know the shear force should be 576.47. So this is what this equation is about. So I compute for C1, that's the value of C1. So I can plug into the second equation right here, that would be your final form of the second part of your shearing force. Okay, so it's a linear function going down. Next, if I would like to compute for the moment, I can just take integrals of each part separately. So taking integrals ends up with these three equations. The middle one becomes a second order equation. And each of them has a constant. So I name them as C2, C3, and C4. I need to compute for them. And I know the equation is gonna look like this, because the first part has a positive slope, second part has a negative value for the second order term, so it's going down. And then the third part has a negative slope, so the function goes down when you go right. So at least I know the shape, and the easiest one is C2, because you plug in x equals to 0, the moment equals to 0, so C2 is 0. That's easy. The next part, you just plug in position AT to the first and the second. To the first and the second equation. So when you plug into the first equation, you have 576.47 times 80, second equation, blah, 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 80, plug in 80, and then you can compute for C3. So that will be the result at C3. How do you get C4? You can use the value at 170. So plug in the third equation at 170, it should equals to 0. So you end up with the value of C4. If you are not sure if you are doing this right, you can do like a correction check right between the second equation and the third equation, which is the combination that you have never tried earlier. So that's right at the position of 120. So I plug in the moment of 120, I plug in the second equation and the third equation just to show they should be the same. And at the end, they are the same. So yeah, you don't need to do this. I'm just doing this to show you the calculation is right. Okay? So from here, you realize there's a peak value of the moment. So how do you get the maximum moment? It's a second order equation. If you take a first order derivative and make it equals to 0, that gives you the extreme value. So that's what I did. I took the derivative of the second equation. It ends up with something like this. I make it equals to 0. So it ends up with a position value 96.47. That's exactly where you have the extreme value. So that's where you have the maximum moment. So if you plug in this position into the second equation of your moment, you will get what's the magnitude of that maximum moment. So I plug it in, I end up with 50865 Newton millimeter. So from the problem, I'm asking you drawing the shear diagram and the moment diagram. I ask you to find the location and value of the maximum moment. So you can answer, okay, the location is this guy, the maximum moment is this guy. Then you got full mark. And I remind you to provide the unit. That's it. So if you know how to do it, you can probably finish within 20 minutes, I think. 20 or 30 minutes. This one takes some time to do calculation, a lot of plug-in and stuff. Any questions? Did I make a mistake? Okay. So that's, I can, so please post the solution on Facebook. Yeah, so if you would like to spend some time to read the solution again, yeah, feel free to do so. Okay? Now, get back to today's lecture. If you did not get a good score on the first exam, I will encourage you by telling you that that is the most difficult exam for the course because it requires a lot of calculation in the beam problem. Even I already simplified it. Later on, for the second part and the third part of the lecture, where we are calculating for the design under static load and the design under dynamic loads, they are, I think, easier because there are equations to plug in. You just need to know which equation to plug in. So I think it's easier. But in the second and the third part, I usually apply those equations to a beam problem. So if you are not familiar with the beam problem, you may see it again later on. So please make sure you know what to do for the beam problem. Okay? Okay, let's get back to today's lecture. Okay, so from the textbook, there's a drawing like this, indicating how we can study the failure of different kinds of materials. And in general, there are two kinds of materials. One is brittle, the other one is ductile. So does Taiwanese know brittle and ductile? Okay, good. How about non-Taiwanese? Yeah, I just want to make sure you know the word. Like myself, when I learned this course in Chinese, I didn't know the word ductile and brittle. Yeah. So just want to make sure everyone knows. But how do you identify whether the material is ductile or brittle? So basically, when you try to apply certain force to a material. When the amount of force increases, your material start to deform, and when the material can no longer take the force that you apply, it's gonna fail. So either the failure, there may be different types of failure modes, but let's say, okay, the material is considered as failed. So the amount of deformation that happens when it fails will be utilized to study for strain of failure. So by the definition of strain, basically is the amount of deformation over its original length. So no matter how much deformation it's gonna have when it's failing, that amount divided by its original length, that's strain of failure. So if the strain of failure, basically strain is a percentage. If the strain when it fails is greater than 5%, then we say it's a brittle material. Greater than 5% is a ductile material. So the material elongates larger than 5%, then break. Okay, then it's like a rubber-like. It's a ductile. Okay, but if a material doesn't elongate, it breaks within 5%. Okay, it's brittle. Okay, that's how we quantitatively distinguish whether a material is ductile or brittle. Now, the textbook indicate different kinds of models. Why? Because the way different kinds of material fails, they use different design equations, which are going to be derived based on the solid mechanics of that kind of material. So all these equations are derived based on some kind of solid mechanics theory. And the theory came from how the definition of what kind of material it is. And for us, we are mostly dealing with metal. And most of the metal are ductile materials. So in our lecture, we only focus on ductile material. We don't worry about ceramic or glass, which are brittle. They may meet, then you need different models. But we can still take a look. Whenever there's a design equation, there are two ways you can handle the design. Whether you are conservative or you are not. So what does it mean when you are conservative or not? If you are conservative, it's like you worry about failure. So you want to give the design a lot more safety margin. So usually if you are conservative, if you are a conservative designer, your design should be bulkier, heavier, stronger, but maybe more expensive. Maybe it operates with less efficiency because it's heavier. So I can say I'm a conservative person because I keep my weight up. It's a joke. No one laughed. I'm so sad. It's like making a joke without audience. Okay. So since the way we treat the design in a different fashion, the design model may have different shapes. Later on, when we talk about the models, the function has different shapes. They came from different theory, different mathematical equations. So they usually categorize those equations separately. So as a designer, you can make your decision. For particular design, can I be conservative or not? If we are designing for something that is gonna be related to someone's life. For example, if I'm designing for the cable or the pulley for the elevator, then I need to be conservative because in the elevator we always see the maximum number of people this elevator can take is 10 people, and or the maximum weight is like 1 ton. What if I have some 11 people coming in? It's gonna break some of the wire and we're gonna fall? Maybe not, but try not to do that. Because they usually indicate certain amount of the number or certain value that is related about the load this machine is gonna take. They give you a conservative number. Actually, in fact, maybe the elevator can take 30 people. So it's like there's a 3 times of strength, but they don't tell you how much stronger the elevator is. But it's definitely higher. You don't want to take a risk, so they tell you, okay, keep it lower than 10, you should be fine. The elevator can operate for 5 to 10 years. But if you always have 20 people coming into the elevator every day, every time, maybe some of the wire could be breaking earlier. So usually as a manufacturer, we will specify how much time, what they will estimate when the material is gonna fail. It's some number no one knows. How can you predict how long this? Tell me exactly what time this table is gonna break. No one knows. But as a manufacturer, we have been making this table for 1 million pieces. And we already have product historical data we know, and also we may have some analysis on the structural strength and so on. We know approximately this table is gonna last for 5 years. Let's say 5 years. So it's like the true time this table is gonna fail is unknown. It's an unknown value, but averagely or approximately, I know maybe it's gonna fail 5 years later. So that's designed for that particular 5 years. And if I want that average time to failure to be longer, I want to lengthen that life of 5 years to 10 years, I may need to make this table double stronger. So how do I make it double stronger so the mean time to failure is gonna be doubled? That's the job of a mechanical designer. We need to know the mechanics and design rules so that we know we can estimate if I make this part thicker, if I apply another bolt right here, or I make the metal part 1 centimeter thicker, I guarantee it, the life is gonna last longer, double the longer. So that's our job, okay? So, if you want to be conservative, I make it with longer life, but bulkier, more expensive. I will be making less money because I use more material. And since I use more material, I will be charging for a charging for a greater price. And this product will be less competitive in the market because it's more expensive. So there is always a trade-off. Performance and strength. Okay? If I would make it strong, it's not stronger the better. Stronger may mean more expensive, more waste on the material, and you cannot make a deal. You cannot sell it in the market. So as a designer, we need to decide how conservative we are. And it depends on where you apply it. If it's related to someone's life, definitely bring up the safety margin. If it's something you don't mind, like this particular part, if it breaks, it's not going to kill me. It's not going to kill the teacher if this stuff is breaking. Okay, then maybe the safety margin doesn't need to be high. Because as a designer of this container of markers, I believe regular human, usual people right here won't sit on this. So there won't be 50 kilo of weight applying on this container, so it won't be breaking like unusually. So even though someone is doing something crazy and doing this, and it breaks, it's not going to kill the person. It's just gonna hurt someone's butt. Okay, thank you for laughing to the joke. Okay, so yeah, maybe when we design for the container, we don't need to be conservative. Just make it cheap. Okay? So when we are dealing with ductile materials, if the way the material behaves similarly when it's under tensile force and compression force, then it's like the material behaves the same when it's having a positive force or a negative force. Then mathematically it's easier for the design. Because later on when we talk about the equations, the design equations covers the design space on the positive side and also the negative side. And those design equations have some kind of symmetry on the positive side and the negative side, which means those design equations handles the same handles the force is the same when it's a tensile force or compression force. They have this kind of symmetry behavior. So if this is yielding strength for tensile and yielding strength for compression is very close to each other, we treat them like there's a symmetry on material property. So we will handle those in the following equations. But there is a unique kind of material where these two yielding strengths are not the same, which means a material behaves differently when it's carrying tensile force and compression force. So you may need to handle the tensile part and the compression part separately. You may need two sets of equations. So for those, okay, let's do something else. But in our course, we handle the material type where the compression and the tensile behave similarly. Okay, the yielding strength is the same. And then we will make a decision whether we are conservative or not. So then we have different equations. Later on, I will also cover basically there are models. This is a maximum shear stress model, this is maximum distortion energy model, and there is another so-called maximum strength energy model. So I will be covering 3 different models, and they have different levels of conservativeness. So which one is the most conservative? This one is the most conservative. Okay, and which one is the most, how do you say the opposite? What's the opposite word of conservative? Not conservative? Okay, not conservative. Okay, which one is the opposite, the most opposite of conservative? That would be the strain energy. So this is the least conservative. The strain energy model is the least conservative. And the distortion energy model is kind of at the middle. But it's more, it's basically in the middle, okay? I can kind of show you what's gonna happen later on. We're going to learn, not this one. I just want to show you. Then we figure out how to derive for those. Maybe this one. Yep. Right here. So this is what we will be learning for at the end. There will be a design equation like this. At the end. So we mostly handle plane stress problems, and we will be focusing on the major stresses on the plane, in a plane. So you have 2 principal stresses, 2 major stresses, and we indicate them as stress A and stress B. And we will be forming design boundaries later on. So what are those? Those are boundaries for your design. So it's like, if my material is carrying some kind of load, there could be some loads along the A direction and also some loads along the B direction. They could be positive or negative at the same time. So if my design ends up with stresses, both positive, then my design point will be somewhere in the first quadrant. As long as that design point is not reaching toward the boundaries, I'm fine. And over here, you can see 3 different kinds of boundaries. One is shown by this dash, like a weird shape. That's the most conservative model. Why is it conservative? Because we only allow the stress to be as large as up to this level. We don't allow the stress to be greater than this dashed line. So that's the most conservative. It allows smaller amount of stress. The second model, the blue one, can take a little more greater stresses. The red one can take even more. So which one is correct? Depends on how conservative you are. So if you are conservative, then use the most smaller design space. If you are not, you are least conservative, okay, then use the largest one. So what does those design boundary mean? When you are carrying certain load, leading to certain amount of stresses, and if you are able to make a point on this diagram, and when that design point reaches to the boundary, the material is about to yield. So that's the exact moment the material is gonna yield. So what do we do as a designer? We gonna design our loads that is far away from the boundary. So later on, we will introduce something called safety factor. We know where the limits are, but we don't want the design to reach those points. Because when the design reaches to the boundary, it yields. So let's just keep it smaller. Just shrink the design space a little bit. By doing so, in fact, this is the final form of what I'm going to teach for this part. We have smaller design space. If my design point ends up with somewhere on the boundary, it won't yield because I have a safety margin. If it's about human's life, I have greater safety margin. If it's something we don't mind, okay, we can have a smaller safety margin. That's it. Okay, and what does the stress relate to? What does the stress relate to your design? So every time you have a stress point, it's gonna relate to the material property. So the material based on your choice, if you use a strong material, of course it's gonna be stronger, a weaker material, weaker. And geometry. So if you design the object in a weak shape, then it's gonna carry a large load. If you design it properly, the stress is gonna be smaller. Right? So geometry. What else is real? And also how much force that you apply to the design. What else? Nothing else. So if I design this table, I can use plastic, I can use metal, I can use wood. So different material choices. And then geometry. I can design this with certain thickness. I can make it thicker, I can make it round, I can design it in different shape. And then I can apply load. Okay, a person's total weight applied to the table or 10 people applied to the table based on your design. So those are the choices. So based on the choices, it ends up with some stress value somewhere inside the material. So do I analyze everywhere? No. You only need to analyze the position with the maximum stress because that's where the material is gonna break. That's why in the first part of the lecture, we need to figure out where is the position of the maximum stress. So for that particular design point, now figure out whether that design point is inside the design boundary, safe boundary, or about to the safety limit, or even up to the yielding point, or even already over. That's basically what this course is about. But whatever we are going to be learning today, and also some of the lectures in the following ones, we only handle static loads. So basically, if I apply a load, it's there all the time. So it's under the condition of static load. The amount of the load doesn't change with time. And once we are finished with this part of the lecture, later on we will be moving on to the dynamic load. So basically, you will be applying loads in some kind of fluctuating fashion. So the amount of load change with time. In that case, a different material, like a material behavior happens. It's so-called fatigue. So how come a material could be having this kind of property, so-called fatigue? Because when we realize when a material is carrying dynamic loads, the amount of the strength gradually drops. Because it's getting weaker and weaker when you have this dynamic loads. So it gets the stress reach to the yielding more easily if you apply more rounds of dynamic loads. So this reminds me that I should not meet my student too often. Otherwise, they will fatigue. Okay. But as long as they don't break, it's still safe. Like sometimes my daughter will come home. She'll say, "Oh, I'm about to die." I will tell her, "That means you're not dead. That means you survived. You're still under a safe margin." You are not yielding yet. You're just complaining. Okay, anyway, get back to the lecture. Now, we are going to cover today only the first model, the most conservative model, so-called the maximum shear stress model. And later on, you will see those dash straight lines to form that design boundary. Okay, so how do we derive those straight lines? First, we're going to recall Mohr circle for tensile test. I told you this earlier. We are going to talk about Mohr circle when it's doing tensile test. And the Mohr circle looks like this. And when it's carrying a normal tensile stress only, the Mohr circle looks like this, and the second principal stress remains zero. The first one gets bigger and bigger when you apply greater loads, until a certain moment where the maximum, the first principal stress equals to the yielding strength. Then the material is about to yield. So what's the limit for this tensile test? So when S1 is about to reach the yielding strength, your material is about to yield. So the allowable shear stress is gonna be half of the yielding strength. Why is that? Because for a Mohr circle, this is your tau max, right? That's your maximum shear stress. So this is why this model is called the maximum shear stress model. So during the tensile test, the maximum shear stress enlarges as the pulling force enlarges. So when the material is about to yield, S1 equals to Sy, and right at the moment, your maximum shear stress equals to half of the yielding strength. So remember that. We have this design equation. That's why later on you will see some equation. How come the yielding strength is divided by 2? This is why. Okay. Next. Now, so let me remind you that in general, whenever we draw a Mohr circle, we are focusing on the stress condition within a plane. But in fact, for every material, we can study the stress analysis along 3 different planes. So it's like if this is a material, and if this is the first, second, and third direction, I can studying on this particular plan, I can study on this particular plan, and I can study on this particular plan. So plan 1, 2, plan 2, 3, and plan 3, 1. On these 3 different plans, I could be doing Mohr circle analysis and making a drawing like that. At the end, that would be the general Mohr circle. So in fact, in this particular case, if you have because we are dealing with plane stress problems. So let's say the third one equals to 0. So that's a plane stress problem. The third one equals to 0. So in this particular case, what would be the amount of your maximum shear stress? When S1 is positive, S2 is positive, negative. In this case, the radius is gonna be S1 minus S2 divided by 2. So in this particular case, the design equation for maximum shear stress model becomes this. S1 minus S2 divided by 2, and it has to be smaller than half of the yielding strength. Okay, so if you agree with this, let's take a look at the next equation, next case. So when a material is carrying certain different kinds of loads, maybe the first and the second principal stresses are both positive. And the third principal stress remains 0 because it's a plane stress problem. In that case, the Mohr circles look like that. And when we have a Mohr circle like that, what's the maximum shear stress? Basically, S1 minus the smallest one, which is S3, but S3 is 0. So at the end, I will have S1 divided by 2 smaller than S2 divided by 2. So in fact, it ends up with some equation S1 smaller than Sy. But what is SA and SB? So here's the thing. When we are dealing with a planar problem, we can assign coordinate to the planar problem if they are aligned with the principal stress coordinate. I can say, okay, one of the direction is A, the other direction is B. And once I label them as A and B, maybe in one particular case, as A is larger, in some other particular case, as B is larger. So when we do the Mohr circle, this is more like a general case. We always name the largest one S1. But S1 sometimes could be the one along A coordinate, and sometimes it could be the one along B coordinate. That's why we need to categorize this exact same equation into 2 different types. Because there is a material where we put some labels on top. Okay, this side is A, this side is B. Okay, you stay as A all the time, you stay as B all the time, but sometimes A carries larger load, sometimes B carries larger loads. And we treat the largest one as S1. So S1 sometimes is SA, S1 sometimes is SB. But the design equation, the Mohr circle is always like this. It's always the largest one that has to be smaller than or equal to Sy. So sometimes it's SA smaller than Sy, sometimes it's SP smaller than Sy. That's why one equation leads to 2 equations. I'm not sure if you get me, but anyway, I hope you can understand it. Anyone okay with this? Okay, now more of those. So here's the situation, like I mentioned earlier. One of the principal stress is positive, the other one is negative. So earlier we said the equation equals to the large one minus the smallest one, S1 minus S2, divided by 2, and this has to be smaller than half of the yield strength. So it ends up with an equation like this. The largest principal stress minus the smallest principal stress smaller than Sy. But like I said, this could be SA, this could be SB. So it leads to two equations as well. Okay? Similarly, we do it again for case 3, where both of them are negative. So now, when we deal with the case where both principal stresses are negative, the maximum shear stress equals to the largest value minus the smallest value divided by 2. That's what this looks like. And S3 equals to 0. So it ends up with negative, the smallest principal stress, smaller than yielding strength. And this guy could be SA or SB. So these two equations. At the end, we have 6 different equations. And if you try to draw them in a figure where the horizontal axis is the stress along the A direction, and the vertical axis is the stress along the B direction. These 6 equations could be drawn like this in this SASB diagram, and they are, how do you call that? The polygon with 6 edges. Ends up with something like this. So this is the design boundary for maximum stress model. It's not one single equation. It's a boundary formed by 6 different equations. So how do you use it later on when you design? If one day you're solving any problem and you can draw the Mohr circle, no matter what maximum shear stress you're having, that can be directly used for your design. So whatever design you have, as long as you can compute for the maximum shear stress and just make it smaller than half of the yielding strength, then you're fine. Because whatever load condition you're having, if you have a Mohr circle and you have a design equation like this would be one out of 6. This equation represents 1 out of 6. So this is just a very general case, and trying to graphically show you what the design space look like in a general fashion. But calculation-wise, later on when you do design, just use this. Just do the Mohr circle. You will do Mohr circle analysis, and you can compute for the maximum shear stress. Just make it smaller than half of the yield strength. That's your design equation. Okay? Making sense? It's not so difficult. Okay, now we're going to apply a concept of safety factor. So how do we apply safety factor? So basically, we will be applying a safety factor at the bottom of the right-hand side. So just make this right-hand side divided by a certain value called n. So n is your safety factor. So whenever we want to consider some safety factor, we just divide the right-hand side by n. And n has to be greater than 1. So in the future, when you see someone saying, hey, I have a design with safety factor of certain value, and if you see that safety factor is not greater than 1, either the person is doing something wrong, or the person is having an unsafe design. Okay? So safety factor, it should be some value greater than 1. So that gives you a safety margin away from the border. That shrink your design space a little bit. So you are only allowed to design your whether material or geometry or the force in a certain way, so those stress points can only reach up to the red lines, and you won't reach to the dash lines. So you are still having a safety gap between the true value, which is yielding. You still have some margin. So if one day, when you realize let's say you design this geometry as 1 centimeter thick, and when you produce it, when you manufacture it, in fact, it becomes 1 millimeter thinner than your expectation. So originally it should be 10 millimeter, but it ends up with 9. So if you are thinner, your design should be weaker. But if you design the table right on the red line, in that particular case, when it becomes weaker, the stress will be slightly larger as long as that amount of greater stress is not over the yielding point, then your table design is still safe. So that's why we would like to have some safety margin, because we may have uncertainty in material property, in geometry, and the amount of force. Let's say my weight is 95 kilogram, but maybe this morning I had a big breakfast. So in fact, they give me 1 kilogram more in weight. And then I don't know, I thought I'm 95, now I'm 96, and then I'm doing this. It probably will break the table. So everything could be uncertain in reality. The material property, okay, when you buy metal, it tells you the Young's modulus, yielding strength, ultimate tensile stress, and all the material properties. But you won't be measuring those. In fact, you won't be measuring those. Can you believe the numbers? Maybe the piece you receive is slightly different from the value they told you. Maybe it's slightly weaker. So you need certain safe margins so that later on when you do your design for your machine, you are okay. You need safe margin everywhere. Okay? So now if we apply to a beam problem, this is like in one of the examples that I showed earlier, this is right after the principal, the Mohr circle in the principal stress analysis. We realize there is a position where it's carrying the largest moment. So I did the calculation for stresses and also the shear stresses. So I have maximum shear stress, principal of first and second principal stresses. So if I apply maximum stress model, basically my shear max is here, has to be smaller than or equals to the yielding strength if the material has the yielding strength of 350, apply right here, divided by 2 over n. So it ends up with a value n smaller than 13.89. So what does it mean? This means this design now at most has a safety level of 13.989. So it's like if you are designing this equation in a certain way, you end up with a solution with a boundary n smaller than or equals to a number. That means your design has this amount of safety at most. It cannot be safer. It could be weaker, but it cannot be safer based on whatever design that we had earlier and the material property that I chose. The safety level of this design is this value. So let's say if I change the material property by a half, if I use a cheaper material and I reduce the yielding strength by half, what at the end is going to happen is this is going to be half of it. So it's a 6 point something. So because I change to a weaker material, the yielding strength reduced by half, so my safety level reduced by half. So at the end, the design only has a safety level of 6 point something. But if I keep on reducing it, and until one day this safety factor will end up with some value smaller than 1, that means this design is going to yield. Because n equals to 1 means about to yield. Okay? Greater than 1, that means you still have a margin away from yielding. Smaller than 1, that means you're more than yielding. Okay? So that's it. And of course, when we have this design equations, we can not only design for the value of n, because take a look at those values. Normal stress could be computed by 32m over pi d cubed, right? And a tau could be computed by the 16t over pi d cubed. So over here, tau max is related to the stress values and the tau values. So if I make a decision of D, if I make the geometry larger, so over here the bottom becomes larger, so the stress decreases. If the stress decreases, maximum shear decreases, so safety level increases. So now you can see how those equations are related. N is the more bending moment you apply to the shaft. You can now change how much force you apply to it. So the moment could be reducing. If the moment reduces, stress reduces, maximum shear reduces, so safety increases. So right here, this is related to the external load. This is related to your geometry, right? And this is related to your material property. And this N is related to reliability. How reliable this design is. So overall, when we have mechanical design, these 4 things are tangled together. Material, load, geometry, and how much safe you are looking for, reliability. That's it. That's it for today. Am I finishing too early? Oh, I did make some examples. Right here, earlier it was steel. If I change the material to PLA, if I 3D print this object, and I Google for the yielding strength of PLA, I end up with a safety factor of 1.04. So the shaft, PLA shaft, is about to yield. And what is this? This is exactly what I want to say. You can now figure out design equations. This is exactly what I wrote. You can plug in design equations. So you can actually have equations like these, and you can say, hey, for PLA, can I change the dimension of the shaft so I can reach a safety level of 3? So now safety factor become a design goal. I want a design with safety level of 3. So what do I change? I keep it as the PLA, so the yielding strength is the same. So, and also I want to carry the same amount of load. So the moment and the torque is the same. So what do? I enlarge the shaft. So only thing left is D. At the end, D has to be almost 50 millimeter. So earlier it was a smaller shaft. If I make it by 3D printing, I need to print it thicker. Okay? Yeah, that's the end of my slide. Any question? So from here, you can kind of guess how the exam is gonna look like. Okay, and I will give you equations because you won't be able to memorize those. How can you memorize those? No, right? No one can. So I will be giving you equations. That's why I think the later exams are easier because it comes with equations. But I know for some of you, you still may think it's very difficult because there are so many knowledge accumulated in one problem. So it's getting more and more accumulated. This problem can be even more complex later on. Why? How? There's something called stress concentration.